Let's actually do an example problem of how we can actually use a lot of this math in the real world. Uh, so this one focuses on price breaks, which are very common in a business where you charge something for a particular margin or interval, and then the rate of which is charged changes. Like, for example, with bulk orders, you might charge less per item than ordering single copies. And there's same with shipping, it might depend on the weight. There's a lot of instances with business where you need a piecewise function to describe the breaks within costs. So let's just read the example and then we'll start working on it step by step. So it says Jock Rocks sells decorative landscape rocks to fraternities in bulk quantities. For quantities up to and including 400 pounds, Jock Rocks charges $3 per pound. For quantities above 400 pounds, JR's charges a flat $100 plus $2 per pound. So we have a ridiculous problem that I probably made up and I thought was funny at the time. But basically, we have a couple different situations. It's like when it is up to 400 pounds, they charge flat up, straight up $3 per pound. But when it gets larger, they charge less per pound with a flat cost of $100. So in a piecewise function, let's just call it P of X, well, because it's here in the packet. But another thing we'd want to know is, well, what does X represent and what does Y represent? But really what we can tell is the variation in cost is dependent on how much the customer buys, right? In this case, it's pounds they purchase. So that we should set to be our variable here, the independent variable X. So I'll just go ahead and note that X is equal to the number of pounds the customer purchases. And one of the things is that they're going to charge $3 per pound, or basically $3 times X. The more they buy, the more, it's $3 per pound. So that's going to be the first part of our piecewise function, the first branch, 3X. So, say they buy 100 pounds, they're going to pay $300, and that would be represented by 3X, right? 3 times 100. But that's only going to be the case if X remains less than or equal to 400 pounds. So again, we get a sense for the boundaries of our piecewise function, or the domain for each piece. The first piece was only up to and including 400 pounds. That would be something we would need to know, obviously, in order to write the function. And so there's those components. What is the formula for calculating the price that they're going to pay? And then what is the mathematical relationship both are involved? Now, for quantities above 400 pounds, so if the customer is purchasing more than 400, not inclusive though, because you don't want it to have two different prices. There can't be an overlap within the domain there. It says that Jock Rocks charges a flat $100 plus $2 per pound. So basically, it's going to be 2x because that's our variable. The more poundage that they buy, they're going to pay only $2 per pound, but also they have this flat cost of $100. And that is going to be a function which describes the price breaks here. Another question would be, if we're trying to set up a pricing system for our in this case our decorative rocks, do we want a discontinuity? Discontinuities are a little bit strange. Like, if you can imagine, let's say I'll just draw a graph that has a discontinuity so we can discuss this idea. But let's say that the price of our item looks something like this, or whatever. A discontinuity is a little unusual because it's like at a certain point the price gets way more expensive and has a break, or let's say it got less. Like, any point of discontinuity would be very strange in a pricing system, because why would the customer ever go for those points where there's an immediate jump? It makes way more sense to pay less. Or why would a customer ever pay from something right here if it costs them less later? So it's like, you want a pricing scheme. Discontinuities usually are not ideal because they're just silly. It doesn't lead to anything sensible for anyone. And that's kind of the idea of this question, is we can check for continuity and see if this is any good. So like step 3 says, is P of X continuous? So what we could do is just check using the same tactic in the previous video. We could set them equal to each other and plug in the point value of where it changes at 400 to see if it actually is equal. So, and again, these are both just linear functions, so they would be continuous on their domain. The only potential place that they could be discontinuous is at the 400, where it switches from one piece to the next. And what I can see here is this is 1200 on the left-hand side. Or essentially, if they were to purchase 400 pounds, well, technically they would have to purchase less than 400. The left-hand limit here would be approaching 1200. The right-hand limit here would be approaching 900. So those, again, are not equal. So that means it is not continuous at x is equal to 400. And when we see our graph, we can expect to have a weird discontinuity there. And it says use a calculator to graph it in this particular window. So this is a good opportunity to discuss how do you customize your viewing window for a real problem? Because if we were to just graph this, type this into our calculator, the issue is usually the screen graph stuff from -10 to 10. The viewing window has a very specific domain and range based on your average mathematical function. But you can actually customize a graphing calculator to show anything you want and expand it for real problems where your customer's probably not going to just buy up to 10 pounds. They might buy 1,000 pounds. They might buy 4,000 pounds, and we want to see a better window of this correlation. So if we want to do this, we need to start by typing in the piecewise function. So we're going to have 3x, and that's going to be if x is less than 400. So I'm just going to go ahead and edit this. And then also, it doesn't really matter if I change it to less than or equal to. This is a workaround to get the calculator to display it anyways, so I'm just going to be a little lazy here. And then in the second piece, it would be 2x plus 100. So I'm going to go ahead and insert that. And then that's only going to happen if x is greater than 400. Close that off, and that should be my piecewise function. Now, if I just graph this in the most basic window, I'm going to see really what's happening from -10 to 10, but that's not what I care about. And here I've given you a sample window which could help, but basically it says graph it in the window of 0 to 1000 by 0 to 2000. This is a fairly common notation for, it's basically, here's the domain of this function that we want to use in a graph. Basically, negatives don't really make sense here, right? Because a customer can't purchase a negative amount of pounds. I mean, I guess they could sell it to you, and that might be like, instead of buying, negative is always the opposite, so selling, but that's silly. So let's just say we're letting our window be, well, anything from 0 to 1,000 pounds of rocks they're going to purchase. And it says to use 0 to 2,000 as the range. Just that would be how much they're going to pay. And again, I've given that here so we don't have to think about what it would be in a sensible setting. But basically, if you go into window on a TI-84, you can customize exactly what is shown, where it will say X min and X max. Basically, that's like, well, what do you want your X-axis to show? Here we want from 0 to 1,000, as we were told. And the X scale will affect the tick marks on the graph. If you leave this to 1, basically it's going to give you 1,000 tick marks in there, everything from 0 to 1,000, which would look bad. So what I'm going to do is just going to set it to 100. What that will do is every $100 or every 100 pounds, it will make a tick mark, and I can kind of see what's happening a little bit clearer. And Y min and Y max, again, this will be the range of our view window. We want that to show from 0 to 2,000. And in the same way, let's just set the scale to 100 so that will fix that's what SCL stands for, is just X scale, Y scale. And the resolution you don't need to bother with. Now when we graph it, we will see more clearly what our relationship looks like over time. So let's go ahead and create a sketch of this situation, or this piecewise function, based on our graphing calculator. But essentially we have a linear function over here. It has a slope of 3x. For every pound they purchase up until 400, they're going to be paying $3 to the pound. Then all of a sudden it jumps to $2 a pound plus flat 100. And once it surpasses 400 pounds, it's going to be a less of a slope, $2 per pound instead. And again, we know that this is going to be a solid point, and this would be an open point just based on the greater than and less than symbols in our function, because that was what was told to us. And we know it's discontinuous because, we've already skipped ahead, but we could also see from the graph. Now, the last couple questions says, if not, where is the discontinuity? So It was at x equal to 4. Or 400. We already answered that. And also, what does it mean about the limit there? If it is discontinuous, it technically doesn't mean the limit doesn't exist. If it's discontinuous, it means either the limit doesn't exist, or the function is undefined, or the limit does not match the function value. We do know the function is defined at 400 because it says so right here. It's going to be $1,200. We know that for sure. But what we already kind of figured out was that the limit doesn't exist because, you know, when we're coming from the right hand side, we're headed towards 900. When we're coming from the left hand side, we're headed towards 1200. So let's go ahead and sketch that out below. But basically the limit as x approached 400 from the left hand side of p of x, that was equal to 1200. And the limit as x approached 400 from the right hand side was 900, and those do not equal one another. So I'll go ahead and write it like this. You know, those are not equal, so the limit does not exist. But technically the limit could exist still, as if the function was not equivalent or defined to those, it would not be okay. And this last part of the question could be used in a real problem to say, well, if we wanted to change this a little bit to essentially remove a discontinuity, how would we do that? Like, let's say that Jock Rocks wanted to keep the price margins where it's $3 a pound up until one point, and then it switches to $2 a pound, but they wanted it to be continuous. You could imagine that if you would have raised that flat cost, you know how it costed, it was $2 a pound plus 100. If we change that value, or obviously we could change the slope of it as well to fix that. But if we want to keep those slopes consistent, it's basically like, well, is there a way that I could change this value, or how I imagine it is raising it up so that it is connected and that it becomes continuous? Or essentially on the left-hand limit, we know it hit 1200. So what could we change 100 to make sure that it be continuous? So here, since I know the right hand limit was 900, basically if I added 300 to that, that would raise that right line up a little bit to make sure that it hit together. So let me just sketch out what I'm thinking below, and I'll just write the answer. But basically it would be 3x if x is less than or equal to 400, and then it would have to be 2x plus $400 if x was greater than 400 instead, because that would ensure that at that point of 400 you're gonna keep the charge of $1,200. And then here, once you switch over to $2 per pound, if you add 400 at the point of 400, you'd have 800 plus 400, 1200. It would be equal. It would satisfy this equation. And basically I was saying, you know, I could identify how much I need to add by looking at the discrepancy between the 2 points, as I did with step 3. But you could adjust these in a lot of other ways, but that's kind of the simplest way to fix that. Now, a customer might look at this policy and say, well, why am I paying this $400 extra? But, you know, if we see the continuity, you can see that it's still beneficial to buy more than $400. Obviously, in the original situation, the major problem here is that why would you ever buy 375 pounds when you could buy 425 pounds and it will cost less or something like that? You know, it doesn't make sense because of the discontinuity. But if we fix the discontinuity, it might seem like you're getting a worse deal by having that flat charge of 400, but actually it's in the benefit of the customer to buy more because you have less costs associated with each pound you purchase.